Okay, before we start skimming through the slides, so again, I just want to remind you. So we were talking last time about, four main families of power converters, right? So we're talking about AC to AC conversion, AC to DC conversion, DC to AC conversion, and DC to DC conversion. So these are the four main families we will be discussing. And before we get into the slides, I'd like to go through some sample applications, and we draw some block diagrams. So as engineers, you need to be drawing. You speak the block diagram language. That is one of the main things you will do as an engineer. Just draw block diagrams. When you read manuals, there will be lots of block diagrams. So when you do your senior design project, you will be drawing lots of block diagrams and connecting them together and showing function using block diagrams, right? So block diagram language is important in electrical engineering. So anyway, before we look at the slide, as we said, we will have AC to AC conversion. We have AC to DC conversion. We have DC to AC conversion, and we have DC to DC conversion. Okay, so now if we have a cell phone application, your cell phone, you would like to charge it, right? And your cell phone batteries are typically lithium-ion batteries. So if you look at your phones, or if you look at the charger of your phone, what sort of voltage level would you see? 3.7. So the lithium-ion, standard cell battery voltage is about 3.7 volts. So this is a lithium-ion battery. And this is very typical of most consumer applications. Lithium-ion this is the same voltage level for pretty much any lithium-ion cell that you would buy. And then you would typically want to charge it from the AC outlet here, right? So which is, we said, 240 volts, RMS, 50 hertz, right? So if you would like to do this, how would you connect these two? Yeah, what type of converters? And you can use multiple ones. You can use ones in series. You can use. Yes, sir. Okay, the physics of a battery, we can get into that. That's why I think I put a battery data sheet on the website. So if you are interested in battery physics, or you're gonna do a senior project with some battery, I think I have a battery. Yeah. So this is a lead acid battery. It's not a lithium ion battery, but yeah, typically, these lead acid batteries that you would use in your car are what? 12 volts, for example. But of course, 12 volts is the average normal operating voltage at a specific load, at a specific temperature, right? So the battery voltage actually varies. And for you to understand how you charge a battery or how you discharge a battery properly, you would need to actually look at the battery's datasheet. So this is a sample datasheet of how, of a lead acid battery. Again, it's not a lithium ion, but there will be similar ones for lead acid battery. So, and it will give you, for example, yeah. So the rating of the battery. This is 12 volts, but what sort of energy can it store is dependent on how much voltage and how much current you can draw. And you're typically going to be given battery size in ampere hours, right? AH, if you see here, it's ampere hours. So you're typically given, you're consuming a certain amount of current for a certain number of hours at a certain voltage. So current times voltage would be your power. So it can consume a certain amount of power for a certain number of hours, which is energy, right? So that's how you specify batteries. It's in ampere hours, yeah. So here they would tell you if you are going to discharge it in 20 hours, and again it has a certain number of cells. So this has 6 cells in series. Each cell voltage is 1.75 volts. So you take 1.75 volts multiplied by 6. That's the battery rated voltage. So if you are going to discharge that in 20 hours, you're going to be able, the capacity of the battery is 7.5 ampere hours. If you're going to discharge it in 10 hours, a lot faster, what happens to the battery capacity? Decreases, 7.13 ampere hours. same battery, but depends on the load, how much you can get out of the battery. So even though it's the same battery, the energy stored will be different if you consume it a lot quicker. So if you consume this whole, if you try to consume all the energy out of this battery in 30 minutes, then all this battery can do to you is 3.75 ampere hours. That is the rating. After that, what's going to happen? It will not explode, right? So if you try to, so even though this battery is 7.5 ampere hours, if you consume this power for along the 20-hour period, if you try to consume it at a faster rate, what will happen is the battery will not blow out, but the battery life will degrade. So instead of lasting for 2 years, it will last for a year. And it's not a matter of time, it's a number of charge-discharge cycles. So let's look at, and it's not only charge-discharge cycles, it also depends on how much you discharge it, so depth of discharge. So this is a curve, for example, showing the terminal voltage with discharge time. So this is if you're discharging it at a certain value of current. So if you're discharging it 22.5 amps in 10 minutes, the voltage will go from 11.34 all the way down to a little bit less than 8 volts. Right? This is just how the battery will perform. If you discharge it in 20 hours, this is how the battery will perform. Right? So, which means the battery voltage keeps changing. Right? So now, if you have discharged it until this point, this is the battery voltage, it's 10 volts. For you to develop a converter to charge it, you need to charge a battery. The batteries don't like to be charged with a current that's not constant. So this is the discharge cycle. This is the charging characteristics. So these are the charging characteristics of the battery. They like to be charged with constant currents. So this is, for example, a charging. This is a what? This is charge current. But where? Okay, so this is the charging current. So this is a charge volume, charge current, charge voltage. So there are three curves here. So I guess this dark one is the current, and then this dotted one is the voltage, and then this charge volume is again the amount of charge that you have put into the battery. So let's look at the charge current for example. The battery likes to be charged with a constant current. If you charge it with a constant current, what happens to the voltage? The voltage starts rising. It keeps rising until at some point it will reach a certain value of voltage. At that value of voltage, you're allowed to start dropping your charge current. This is spec. You can continue charging to the constant current, for example, right? But if you do that, you're not operating within the spec of the datasheet. If you don't operate within the spec of the datasheet, this is what happens to the battery, right? Charge retention capacity. So even though this battery is able to be charged with a certain amount of energy, if you charge it in a certain way, for example, this is depth of discharge. So if you discharge it every time to 50% of its energy, so it was able to deliver 20 ampere hours or 7 ampere hours, you consume it for 20 hours. For 10 hours, you were discharging it at that rate, meaning what? The depth of discharge is now 50%. If you're discharging at a depth of discharge of 50%, the number of cycles of charge-discharge that you can operate this battery for is about 400 cycles. Right? Now you go and design your application. So if you are buying a piece of equipment and they tell you this piece of equipment will last for 2 years, why? I mean, and it's battery operated. This is science fiction, right? It's something that they based it upon what? It's based upon, for example, they believe that somebody buying this piece of equipment will charge and discharge it a certain number of times per year. So they tell you, okay, it's 2 years lifetime, right? If you're in a substation batteries, all power equipment always has backup, and all of this backup is typically battery backup. Yeah. So you would go into any substation, you would find lots of batteries, some battery chargers, etc., etc. So there are people whose jobs are just maintaining batteries, just making sure that everything is fine with the batteries. Why? Because of things like this. So they would monitor voltage, they would monitor, and it changes versus temperature. All of this is at ambient temperature of 20 degrees Celsius. What if the temperature changes? So if the temperature changes, also the data sheet will tell you, okay, the effect of temperature on the battery as well, okay? So it will tell you the effect of temperature on the battery, effect of depth of discharge on the battery, the effect of discharge rate on the battery, everything. So for you to develop a charger is not an easy thing. I mean, it's straightforward if you understand the characteristics of the battery or are able to understand the datasheet very well. So we won't get into, okay, so that's, we get into this because we were trying to talk about the lithium-ion battery. So here we just said 3.7 just for simplicity, right? But we would actually have to go in and figure out, for you to develop a converter to charge or discharge this, fine, you know that this is not a fixed 3.7 volts anymore, it's a variable voltage. So anyway, so you have to make sure that you can develop something that's variable, that allows. Why do you want it to be variable? Because you want the current to be constant. So if this is 3.7 volts, and you would like to charge it with 1 amp, right? Of course, this circuit here will have some resistance. Any electrical circuit, any battery will be represented by an ideal voltage source and an internal impedance or internal resistance. Yeah. So you will have to put a voltage source here. That is, some voltage. This V minus 3.7 volts divided by the impedance of the path. For example, R will give you 1 amp, right? And you have to make sure that is maintained. How is that going to be maintained? By varying V, right? So you will typically have to have these voltage power converters be variable, actually, providing ability to provide variable voltage to the load. Yeah. But for now, we're not talking about details of the power converters. We're talking about block diagrams. So block diagrams meaning, okay, what sort of converters do I need to put in there to satisfy this load? So this is. I first have to start with an AC to DC converter, and you can stop here, typically, and you're connected this way. You can develop a single stage AC to DC converter and do that. We will find that sometimes it is very difficult to develop something that has very big step-ups or step-downs. So this is from 240 volts all the way down to 3.7 volts. You will find that some power converters have limitations on how much you can step up or step down. So sometimes you would end up having to use a transformer in the middle, for example, to step up or step down. Another case is sometimes you may be able to develop, put in here a low-cost AC to DC converter, because you know that after that I need a very controlled current to charge my battery. So typically a low-cost AC to DC converter will not be able to do that. So in that case, you would typically sometimes, instead of just using a single stage conversion topology, you would use a series set where this is an AC to DC converter, where this is going to provide some DC voltage. It's lower than 240 volts, but much higher than 3.7 volts. Probably not controllable because it's cheap. And then you may insert a DC to DC converter in this case. And this DC to DC converter will be lower voltage, be able to control the current into the battery, etc., etc. So there are advantages of this, advantages. What's the disadvantage of having two conversion stages in series from an efficiency perspective? How do you calculate the efficiency of the power conversion stage here? This will have a certain efficiency 1. This will have a certain efficiency 2. What is the total system power conversion efficiency? You multiply them, right? So if this is 0.8, this is 0.8, then you get 0.64, right? So 0.9, 0.9 is 0.81. So even though we have a 90% efficiency for one, the total efficiency is a lot less than that. So at some advantage, some disadvantage. So you may, if efficiency is a concern, maybe go ahead and use a single stage AC to DC converter that's a lot more expensive, a lot more complicated, but will give you a higher efficiency because it's single stage versus a dual stage system. Yeah. So this is one example. How about you want to charge the same lithium-ion battery for your phone, but you want to charge it from your car battery. Your car battery is typically 12 volts, lead acid battery. That's the data sheet that I had on the website. So this is a 12 volt lead acid battery. So what would you consider putting in here out of the 4 different conversion stages that we... Exactly. So here you typically, the ratio between 3.7 to 12, is about 3 times, 4 times. So the simple topologies that we will discuss in the class are going to be able to give us this 3 to 4 ratio between input and output with a good efficiency, right? They will be able to do that. So here we'll typically be doing a DC to DC. I could have used the linear regulator like we did last. We talked briefly about the linear regulator last time. It's a simple linear regulator like you studied in 325. We did this, and we said that what is the efficiency of the linear regulator? What? It's power output over power input. The current is the same, right? Since it's a series circuit, so it's voltage output over voltage input, right? So it's 3.7 divided by 12 volts in this case. What is that? 0.0308. Yeah. No, 0.03?
0.308.
Yeah, 0.3. Yeah. Not 0.3. Because 0.08. Yeah. So, about 30%. Right, this is 30%. So this, we will design converters like this in the class, and we will see that we can do this with efficiencies way above 90. So this is something we will be looking at. Okay, so another application. A camera flash. You'd like to run your camera flash. So how does the camera flash work? So typically you have a lithium-ion battery that's 3.7 volts in this case. And typically camera flashes are sort of capacity 300-400 volts. Yeah, it's a high voltage device. I will just put this as to resemble the camera flash. And what happens is you typically charge a capacitor here up to 400 or 300 volts, and then you remember your transient response stuff that you did in 214, and then you close the switch. After you close the switch, what happens? All the energy stored in the capacitor will be placed across this flash, and you get a lot of energy instantaneously on this light bulb, and it glows. Yeah. So here I need 3.7 volts. I need to step it up. Right. In the previous application, I had 12 volts, and I was stepping it down to 3.7. Right. I needed a step down converter. Or what we call it also, we call it a buck converter. We will talk about that later. But here I need a step up converter, right? I need to take my 3.7 volts and I need to step them up to 400 volts, DC as well, right? So I would still use here, for example, a DC to DC converter. Right? So that's what this topology would be. Again, this is a huge step-up ratio from 3.7 to 400. We will find that the simple topologies that we will discuss, there are 3 basic topologies that are the basics of the more advanced topologies. But the basic topologies can only do step-up ratios of about 3 to 4 times. So from 4 to 16 volts maximum. Right? So something like this would be more complicated than the basic topologies. Right? But it's still doing the same thing, DC to DC conversion. But it will be a more complicated circuit topology to, maybe it will have a transformer in there, maybe it will have more than one stage, whatever it is. But at the end, it's still a DC to DC conversion stage. How about a PV system? A grid-connected PV system. Here I have my photovoltaic panel that is giving what? What sort of output does a PV panel provide? DC 12, 24, 48, depending on the panel, right? So it's, let's say 12 volt DC, and then here you want to grid connect it, so it's 240 volt RMS, 50 hertz is what you have. So what do you do in this case? This 12 volts to 240 volts, right? So if I'm gonna remember the discussion I was saying, the basic topologies will probably not be able to step up more than 4 times. So which means here you can use a DC to DC converter. I can sorry, not DC to DC. What do you use here? I can use a DC to AC. I can use a single DC to AC converter, and there's a lot of research work on that, and there's a lot of work on that and how to come up with topologies to make this happen because of the large step-up ratio. So there's a large step-up ratio that you require here, and this is DC and this is AC. So this is one way to do it. The other way to do it is what? Here, 12 volt DC, and then I can use a DC to DC converter to step up this 12 to something like more like from 12 to what? I can step it up to 60, 100, whatever it is, and then or I can step it up to something even more higher than 240 volts. Because again, this 240 volts here is not really 240 volts fixed, right? It goes up and down, right? So then you typically need something, if you're gonna be interfacing to this, you would want something that is capable of providing more than 240 volts RMS, or less than 240 volts RMS, right? So you may end up putting a more complicated DC to DC converter stage here, and then maybe a simple DC to AC inverter, or a more complicated DC to AC inverter, and have a single stage power conversion architecture. So these are two architectures, and they're both used in industry. Today you will find this and that. Some companies promote this, some companies promote that. So there's no right answer, wrong answer, right? What else? How about electric vehicles? Since there's a lot of discussion about electric vehicles. What about electric vehicles? So you typically have a three-phase motor drive that is going to provide torque to your wheels, and this is three-phase, it's AC, and it's variable voltage, right? Variable voltage and frequency, right? So, and this is typically a battery bank that is, I think the Tesla is 300 volts. I'm not 100% sure yet, but I think the battery bank of the Tesla is about 300 volts. So what do you do here? You will use an inverter. So it's a inverter, or also called DC to AC inverter. So it's a DC AC converter, or we call it an inverter sometimes. So sometimes we call the DC to AC inversion or converter an inverter, and we call the AC to DC converter, we call it a rectifier. But they're all power converters, so it doesn't really matter what you call it. Yes, sir.
Three-phase rectifiers and inverters?
Yes. Yeah, we will study it. One form of three-phase rectifiers, one form of three-phase inverters. Right? There are so many. So we will discuss one type, or one or a few types, but not everything that's out there yet. What else? I saw a BMW i8 here in Qatar. I saw one. I don't know. I didn't see. I don't think I saw any Teslas though. Not yet. Yeah. There's an i8 in Qatar. I think he works at Ras Gas. I'm not sure. I think I saw it coming out of the West Bay, the tower, Tornado Tower, West Bay. Yeah. I don't know where at home. I guess he charges it. Yeah. Okay. What else? How about air conditioning system? HVAC. Air conditioning systems. Sure. So it's typically a compressor that's a motor driven. It's either single phase or three phase. Three phase for a building like this, it would be a three-phase motor. For maybe a small unit AC, those window ACs that you have in your homes. These would be single-phase motors in that case. But in this case, of course, we're running off the three-phase AC grid. If it's three-phase, I can just draw that like this. And so this is the AC grid. And this is variable voltage and variable frequency as well. And this is a fixed voltage and a fixed frequency. So you would need to put something here that converts AC to AC. That's one way to do it, is AC to AC conversion. And there are topologies we will take for that. We will find that the topologies we will study for those are not very well suited for highly controllable applications that require proper control of the motor speed. They are good for motor starting, like we talked about. There are topologies for AC to AC conversion, direct AC to AC conversion, that are in research phase, but they've been in research phase for 15, 20 years. They're not commercially viable. So the workhorse in such an application is actually to take this AC and convert it to DC. So you use a rectifier here. So we convert AC to DC using a rectifier. And then this is going to be producing a DC voltage. And then you take this DC voltage and convert it to AC using an inverter. So this will be a DC to AC inverter. This is really the workhorse of the industry. It's not a direct AC to AC converter, even though there's a lot of research on this. I mean, it's been the topic of research for a lot of time, but not economical. So people don't use it. This is much more economical, much more reliable, so people use it. How about wind power generation? So this is my wind turbine, or flower, right? So it's wind turbine. So it's a three-phase motor, typical three-phase generator that produces variable voltage and variable frequency depending on wind speed, right? And then you have, let's say you want to connect this to a single-phase grid. That's 240 volts, fixed voltage, and fixed frequency. So what do you do in that case? Yeah, so this is AC to DC. So you'll typically have an AC to DC rectifier. And then you will typically go for DC to AC inverter. Again, here you could have could have thought of an AC to AC direct conversion. Again, in an application like this, where you have variable voltage, variable frequency in an AC to AC converter, it's even harder to find a topology that does something like this effectively and efficiently over a wide speed range. So one of the important considerations for wind turbines is what? Is very low cut-in speed. You want the wind turbine to start generating power that's connected to the grid at a very low wind speed. So which means very low voltage. So you're operating from a very low voltage to very high voltages at full wind speed, for example. So it's a huge variation of voltage at the input, huge variation of frequency, and then you want to create a fixed voltage and fixed frequency at the output. The AC to AC converter topologies are not very well suited for that. So people end up doing this, and then doing a lot of control. That's where a lot of control, a lot of publications is on how you control these two to effectively work together and stuff like that. And you will see that, okay, there's one way will make it work. Okay, what's the advantages of the other way is fine. It's just another way, or a little bit faster, a little bit slower, a little bit less computational burden on the embedded processor being used, whatever it is. Yeah. So people are really, so these were just some applications, and we gave some block diagrams, etc., etc. And again, you will have to choose based on many things. So electromagnetic interference is one reason. If you're developing something that is going to require a lot of sensors, for example, you do not want you're going to be switching voltage and current waveforms. Anytime you switch voltage and current waveforms, you have electromagnetic interference, meaning you have voltages that are changing considerably. These voltages that are changing, or currents that are changing considerably, are causing changes in fluxes around wires that are going to be linking any coil or any piece of wire that's close by. If you're going to be affecting sensor data in that case. So there is a way to test for EMI. So any product that you actually develop has to be qualified or certified for EMI compatibility, EMI and EMC compatibility, electromagnetic interference or electromagnetic compatibility, that's called. So you sometimes hear EMI or EMC. It's either electromagnetic interference or electromagnetic compatibility. So there are labs that test for that. You cannot just build a product and try to sell it to the mass market without going through such testing. Yeah. Right? So the different topologies, we put a DC to DC converter. each of the DC to DC converter topologies that are available, each will have different performance. Each has a different number of switches, different number of inductors, different number of capacitors. The current shape is different, the voltage shape is different. So each will be producing different kinds of EMI signatures or EMC signatures. Yeah. So the different topologies will differ based on EMI, EMC, for example. They will differ based on audible noise. Power stuff tends to produce a lot of noise because it's a lot of electromechanical interaction. If you pass by a transformer, you will hear, these substations, transformer substations that maybe you have close to your homes or whatever. You will hear a small hissing noise. This noise is because the laminated sheets that are on the transformer are actually, they have magnetic poles that are being flipped. It's AC flux, AC magnetic flux in the transformer. This AC magnetic flux also produces a mechanical force. So this mechanical force actually causes these laminations to be vibrating against each other. And you're holding them together, so they vibrate and they cause some noise. So part of the spec of a transformer, for example, will be the audible noise. When you buy a transformer, that's a spec that you will have to consider. So again, power electronics is the same. So you're causing all these variations in voltage and current waveforms, and you have inductors, you have capacitors, charging, discharging inductors, charging, discharging capacitors will be producing some noise levels. Yeah. So converters will differ based on noise level, efficiency, cost, size, reliability, thermal aspects, and dynamic response. So you can be producing a DC to DC converter from 12 volts, for example, to 1.8. That's fine. To charge, for example, a battery, for example. But you can also be producing this to feed a microprocessor, right? Microprocessors operate, a lot of them operate at 1.8 volts. So if you're producing this converter to run a microprocessor, what is the difference between a microprocessor and a battery charging application? A microprocessor application and a battery charging application. Battery is a very static device, right? There's not really change. Fine, the model of a battery is internal resistance and ideal voltage source, right? You're just charging it, putting some current into this battery, charging it. The voltage of the battery will change very slowly. It takes minutes or hours for the battery voltage to change while you charge it. Yeah, right? How about the processor? How do you buy processors? The current changes as what happens? Exactly. So you have, millions of devices inside. Memory, for example, you have gates, etc., etc. When you buy a processor, they tell you this processor is what? 3 gigahertz, right? 3 gigahertz means what? 3 gigahertz of, this is the instruction cycle, right? So it can do one instruction of code with a frequency of 3 gigahertz. So it can go from one instruction to the next in 1/3 gigahertz time, right? So what does this mean? It means that in the background, when you did your 214 and you did some, or 248 and you did some logic, right? When you were adding stuff or subtracting or storing something in memory or whatever, there were several operations required to do an addition or a subtraction or maybe a few gate applications. So each one of these instructions required a set of devices to operate behind it to be able to get to that point. So switching on these devices requires current or changes in load, right? So the dynamic response here is very important. It's very different because you don't want a power converter that's fine. Your power converter may be able to produce 1.8 volts, but you also qualify it dynamically by putting a load on it and changing what happens when you turn off and turn on a load. If you turn off the load, you're relieving the power converter from providing that power. Turn it back on, you're requiring it to provide that power again. Think of your car, right? Think of your car. If you hit the accelerator, does it accelerate instantaneously? If you have a Tesla, yes, it's very, very fast, right? If you have a Corolla, no, right? So the dynamic response is different. right? It's a car, right? It's the same. At the end of the day, there's nothing wrong with having a Corolla. It's okay. So, but the dynamic responsive converters is also very important. So we actually study this, and you have to you will design converters knowing that okay, this is the dynamic performance based on the switches that I've chosen, and the capacitors and inductors that I've chosen. I decide what the power converter dynamic response is. So which means that you cannot be designing a 1.8 volt converter for a battery charging application, and somebody takes it and tries to use it to run a processor, and it won't work. Of course it won't work because you have not designed it to dynamically operate for such a load, right? So things like that we will discuss in the course. Okay, so now this was the introduction. We'll start going through the slides, through the course material. So any questions? Comments, concerns? Okay. You want to jump up and down a little bit so you can wake up? You're good?
I'm a little sick, so.
Okay. Anyway, so as we said, typically we will call AC to DC rectification, and we will call DC to AC inversion. And at the end of the day, they're all power converters. That's what we discussed. And we talked about dual stage or series connected converters. So you can have a single stage topology or dual stage topologies. Again, the effect on efficiency is important, but if efficiency is not your only consideration, size, for example, may be important, or cost may be more important. So it will depend on your choice of what you put in there. Will depend on what is your metric. So when I first offered the power electronics course, the 438 course, I had students screaming and everything. But what we did in that back then, when I first offered the course, we did not have a textbook. I did not follow a textbook. And what we did was, we were actually designing a power converter, and we were creating a software. At the beginning of the class, at the beginning of the semester, at the end of the semester, you have this piece of software where you can change all the parameters of the power converter, and it will calculate the efficiency. For example, if that's your metric, or it will calculate the size if that's your metric. It will calculate the power losses if that's your metric. I agree it was very difficult to do this course as a first course in power electronics, but honestly, I mean, for me, this is how it needs to be done at some point in your life if you want to become a power electronics person. I mean, it's you need to develop your own sort of design spreadsheets, and you will do this as an engineer. You will always have, for example, 3 different vendors to choose from. How do you base your decision? You will base it on come up with all the metrics, specs, and put them all in a spreadsheet and compare and contrast, right? Same thing with designing a power converter. So you will have to choose your power devices, you will have to choose your control components, you'll have to choose your reactive elements. You put those in there, program it so that you can calculate your metric. And then you base, you choose based on what you want as a metric. If you care about size, you will design it for size. Care about efficiency, you will design it for efficiency. So now I use a more classical approach, following a textbook. So I think it's easier. But hopefully you'll learn as well. So anyway, so we talked about converting from, let's say, from a 9-volt input to a 3-volt output, right? Forget about this resistor for a while, right? If you have 9 volts at the input and you have 3 volts at the output, and this is a resistor value RL. You know that if this is 9 and this is 3, that means I have to have 6 volts across this resistor, right? And this, for me to have 6 volts across this resistor, I can, from there I can choose the relationship between these RL and this value of resistance, and I can plug this there, and I'm done. And I will get 3 volts here, and I'm happier, right? How about if this changes?
The 3 or the resistor value?
No, the resistor value, your load changes. Because you're running, for example, you're charging your battery, and your battery now is almost fully charged. If it's almost fully charged, we saw what happens to the current. The charging current decreases, right? So what do you do in that case? If the charging current decreases, it means your load changed. If your load changes, then what's going to happen to the voltage here? It will also change. If the voltage changes, then I no longer have a DC to DC converter. So what I need to do in that case is make this variable. If I make this variable, then I can sort of maintain. So I can have Bishoy sit here with a potentiometer, and Maryam sitting there measuring the 3 volts, and then they're teaming up to make sure it works, right? That's a very bad way to do it. That's one thing. It's of course manually you cannot be doing something like that. The other thing is, the more important thing is power dissipation, right? So something like this will dissipate power. So I can remove this resistor and do what we did in 325, which is what we call the linear regulator. I think I have a picture of that. No, I don't. So I can remove this resistor and put a MOSFET or a BJT device and operate it in linear mode. What does linear mode of a MOSFET or BJT mean? This was either IC for a BJT device or ID for a MOSFET device, and this was the voltage across the device, either VDS or VDS or VCE, depending on the MOSFET or IGBT. Regardless, it's the voltage across the device, current through the device. What do these curves look like? These curves look like this family of curves. And in 325, what you remember, the load lines, and these load lines would intersect with these curves at different places, and that's how you would choose. Yes. Not why are you saying that? No, this is a BJT. This is you're controlling the base current. If it's a MOSFET, you're controlling the gate voltage. Remember? So with the different base currents or different base voltages, you were choosing. You're operating the device at a certain characteristic, and then based on the components that you put around the device, you were defining your load line. Again, this is 325 material. You don't have to remember it, but think of it this way: you have a device that is. I will draw the device here, for example, and this is plus minus VDS, for example, and this is the current ID, right? So this is the current ID here, and the voltage across the device. I can choose the voltage of the device to be here, 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 based on my operating point, right? I was putting some resistors around the device and making sure that I'm biasing the device in the DC operating point in a certain way to be able to choose my DC operating point, and then you were doing the AC operating point analysis, right? So what does this mean? It means that I can have any voltage that I would like really across a device, right? This is voltage across the device. I can make my operating point anywhere around here, correct? By proper choice of DC operating point, which means I can make a certain voltage drop across my device. And that's how you create a linear regulator. In this case, you create a linear regulator by, you have an input voltage here, and then you would put your device, and you would control it in a certain way, put some device resistors around it, put some bias. I'm not going to draw this. And then if you do that, you're able to change your 9 volts to 3 volts all the time by proper control of this device and the circuits around it. And in this case, you're operating it in this region, right? It's called, for the MOSFET, it was called the linear region. For the BJT, it was called the saturation region, right? So you're operating in this region. When you're operating in this region, it's basically creating a relationship between voltage across the device and current through the device. So you're doing what? You're creating a relationship between voltage and current. And if this relationship is linear, we have this X equal to R, right? And we have Ohm's law. But in general, this relationship is not linear. You can choose any value of, any point here as your operating point, and hence control the voltage across this device to be 6 volts all the time. And hence you're creating your linear regulator that way. You can do it this way, right? And the problem with that, we said, is the efficiency that you lose, right? In power electronics, we don't operate here at all. We don't operate here at all. We use the same devices, but we either operate in the MOSFET, we call it what? Saturation, triode region, right? Call it triode, and we called it cutoff, right? And BJT, which was called saturation and cutoff, right? So what is typical of either operating on this line or on this line? On this line, what's happening? On this line, I have zero current, right? The current is zero for any voltage, positive voltage that I'm blocking. So if VDS is positive, I am blocking the current from going through the device. I'm blocking it, I'm cutting it off. Right? This is cutoff mode. How about in saturation or triode for the MOSFET? What's happening here? There is a linear relationship between the voltage and current. That's nice, because now this linear relationship means I can just have one number here that doesn't change, which I can call R. And we did in 325, we called it R on or RDS on. We took that. It was the slope of this line, right? So this was R, right? And the other very interesting thing is, what is the range of voltage across the device? Is it a big range or is it a small range in this linear mode? Very small. I'm only talking about this small area here. So I'm only operating across with a device where I'm only allowing voltage across the device to be a very small value. So voltage is a very small value. Current passing through it is high. That's fine. Power is voltage times current. So my power across the device would be V times I, for example. It would be, if this is small, then the power loss to the across this device, or the power loss in this device, will be small. But in a linear regulator, I was putting 6 volts across here. And I had the same current. Let's say same current. Let's say 1 amp. Same current, 6 volt, 1 amp. Here I'm talking about 6 watts of loss. Here we were talking about what? You remember what was for the MOSFET? This was the threshold voltage, or when the device was point something, right? 0.2, 0.3 volts was when your device was going to be going into triode region. If you remember the boundary between the triode and cutoff, I think was about 0.3, 0.4 volts for a MOSFET. You were talking about much smaller. So here you're talking about, let's say, 0.3 volts. 0.3 times 1 amp is 0.3 watts. So 0.3 watts versus 6 watts of loss in that case, right? So that's assuming, of course, that if the current is continuous. But, it's a good approximation. This is huge compared to this, right? So in power electronics, we don't care about what was happening in 325 and doing DC operating point, and we do not do this at all. We operate only in saturation or triode and then cutoff, and we typically approximate, since this is pretty close to this line. We typically actually approximate the characteristics as this. We typically say that this is how the device is actually behaving. So there's, this is the current to the device, this is the voltage across the device. Current to the device, voltage across the device. We typically say that the voltage is 0 when the device is turned on, and I can push a lot of current equal to ID, my rated current, for example. And when the device is off, I can block a huge amount of voltage equal to a certain value of VDS rated across the device. It's a good approximation of, this. Instead of here, it was something like this, right? Fine. We typically approximate, and this approximation is for the ideal device, right? Obviously, this is ideal. Since there's 0 volts across the device when it's on, then the power loss is 0. And then there's 0 volts, 0 current through the device when it's off, then the power loss when the device is off is also 0. So which means that the efficiency of this device is 100%. Ideal efficiency of the device is 100%. So if I find a way to make this device create different voltages and operate the device when it's operated in this fashion, then I'm good. I'm so much better than what we were doing with the linear regulators and stuff like that, right? Because now I have an ideal switch that has no power loss across it at all. Yeah. So that's the objective here. So if we're able to do that, then we're good. So how do we do that? So one way to do that is, okay, let's think of this device as a switch, for example. If you have a switch here, I have a 9 volt here. If I close the switch, what is the voltage across my output? 9 volts, exactly. It's 9 volts at the output. If I open the switch, there's no current flowing. There's no current. V times equals the voltage. Here is the I times R, right? R is something, but there's no current, so the voltage is 0. So the voltage goes down to 0. Then I turn on the switch again, close the switch again, and the voltage, the output is 9. Open it up again, the voltage is 0, 9, 0, etc., etc. Right? This waveform is a square waveform. This square waveform has an average value. Like any waveform that is periodic, you can find the average value. Average value of a waveform is 1 over the period of the waveform, integration of the waveform over the full period, 0 to t. The period here is this t, right? This waveform keeps repeating every capital T seconds, right? So I did this integration, and I plugged in 9 here for the value of the voltage that I have, and 0 to t, fine. 0 to t over 3, I have 9 volts, and t over 3 to t is 0, so I don't need to integrate that. So I'm integrating this waveform from 0 to t over 3 over the full period, and then from t over 3 to capital T, it's 0. The waveform value is 0. So if I do the integration, I will get 3 volts, right? Which is nice. That's interesting, because I can get a 3 volt average value. But is my load here seeing a pure DC like the linear regulator? No, with the linear regulator or with this resistor here, this was nice continuous 3 volts. How about here? It's a 3 volt average, right? But it's a pulsed waveform. Can I do this to the load? No, it depends on the load. If I just want a heater for an industrial process, no problem, right? Because power is equal to the average voltage times average current. Average voltage here is 3. Average current is whatever it is, depending on the value of the resistive load, right? So for a heater, yes, it's no problem. It's okay. But for a microprocessor, I cannot. For a microprocessor, I cannot provide 3 volt average value and say that this will feed my processor fine. Because the processor, we said that the processor will change the value of the current that it's consuming at 3 gigahertz frequency. So all of this time, it doesn't even have current. I mean, there's no way that this circuit can provide current because there's no voltage, actually. Right? So for applications, yes. For applications, no. So if you would like to feed a processor, what would you do? You need to be able to create a continuous 3 volt waveform. So how would you do that? What do you know? What is a tool that will take this waveform, which is a periodic waveform, with a 9 volt peak value, with a certain amount of, at a certain period or a certain frequency, and convert it to a smooth waveform, or extract? What tool do you know that will extract a certain component of a waveform from the original waveform? A filter. I mean, your tool is generally a filter, right? So filters are a big deal in power electronics, right? Because they are the workhorse of the power electronics industry. Because you need filters anytime you use power electronics. Because power electronics, what it does is this: chops the waveform. Fine. Here is a simple example where I have a 9 volt battery, but you can have an AC waveform, you can have a 3-phase waveform, you can have many types of waveforms. But at the end of the day, what you're doing is chopping up these waveforms of voltages and currents. Why are you chopping it up? Because you would like to produce some nice average value. This average value can be DC, or this average value can be AC with different magnitudes, can be AC with different frequencies, but at the end of the day, you're chopping up waveforms. So if you want to chop up waveforms and then feed it back to your loads don't like to have chopped up waveforms. Your loads like to have nice, smooth waveforms. So otherwise, a motor will have what? Torque ripples. If you don't provide a nice, smooth current in the motor torque will have a lot of ripple. It will heat up. If you don't provide a nice, smooth current for the lighting system, you will have lots of flickering. Your light will go up and down. If you don't provide that for the processor, it will not operate. All of this. So filters are very important in here. So what we'll do is, yes, provide a filtering stage. What we want to do is extract the low frequency output from this waveform. This is a waveform with an AC content and a DC content. What do I want to see pass through? The DC content. So what do? I low pass filter the waveform. So I will low pass filter the waveform that I have here, and if I do a proper good design of the filter, then I will get a nice 3 volts here all the time, right? And all the time will depend on your load, right? All the time for a processor, all the processor cares about is that between one cycle and the next, the voltage is fixed. So it's not forever. It's just, between one cycle and the next, the voltage is fixed. So the amount of time you have, or the amount of energy required to maintain voltage, how do you charge this? Sorry, go ahead.
The slow pass filter can be only a parallel capacitor.
Sure. In its simplest form, it's just a capacitor. We will see that if you only put a capacitor, sometimes it will affect the shape of the current. So it will make your current that is coming through this switch look like have very high peak value, and for a very short duration. So it will be 0, high peak value, and then 0. So we will see that if you only put a capacitor, this is what happens. But then if you put a capacitor and an inductor, you will sort of do what to the waveform that's passing through the switch before it. You will bring this peak down and spread this waveform over a longer period of time. So you will have the same RMS value, which is going to be representing the amount of energy you have in the waveform, but you will relax the requirement on the switch. The switch will no longer have to see a very peaky current. It will see a lower peak spread over a larger period of time, which is what they prefer to see. Yes, sir.
Is there an equation for the capacitor and inductor?
Of course. You know the equation. What's the equation for the capacitor? What's the equation for capacitor current?
The integral over C.
This is the capacitor current, voltage across the capacitor.
Wait, C dV by dt.
Yes, IC equals C dVc by dt. And then VL is equal to L di by dt. So these are like very important equations that we'll be using throughout the class here. So all the time we'll be using. Yes, sir.
I need equations for the capacitance value and the inductance value if we want to
Yes.
minimize the ripple.
Sure. Yes, we will study that. We will come up with that. But it's based on this as well. It's based on okay, how do you maintain voltage across a capacitor? By pumping in current. So you put in current. If you put in how the voltage across the capacitor is equal to what?
Integration.
1 over C integral of IC dt, right? That's the voltage across the capacitor. So if you pump in current, what it will do, is you will integrate this current and divide it by the value of capacitance. That's the voltage. So what's the integration of flat value? Fixed value. What's the integration of fixed value? Huh? Ramp, right? So if you integrate 5, for example, you will get 5x, right? So you will get a ramp. So if this is the current, right, then the voltage across the capacitor will look like this. When you're pushing this current into the capacitor, this will be the voltage across the capacitor. So do you want the voltage to look like this? You want the voltage to change? You don't want the voltage to change. So what are you going to be doing now? You're going to be smart about what current you put into the capacitor. Now I would like to put in current that may be, what's the integration of a negative value? A negative ramp. So it's a ramp with a negative slope. Assuming if this is 5 and this is minus 5, they're equal, so that the slope will be the same. So then the slope, if this is 5 and this is minus 5, and again, remember it's plus initial condition, right? So let me redraw this and put some initial conditions so that things make a little bit more sense here. Right? So let's say this is my initial condition, for example. If this is my initial condition for the voltage, then until here, the voltage will look like a ramp up, but this current is 5 and this current is minus 5. So I've put in current in this direction, 5 amps, and then I've put out current of 5 amps in the opposite direction. So the voltage will look like what? Until here, the voltage will look like what? same slope, ramp of the same slope but negative, right? Because you integrate a negative number, so you will get a negative ramp. Negative ramp, same slope, because I chose the same numbers and it's the same capacitor, so the voltage will look like this, right? So now this will be what? This is your change in voltage across the capacitor. This is the delta VC. So this is the ripple voltage across the capacitor. That means if you want to minimize this ripple voltage, what do you do? Because you want to minimize the ripple voltage, meaning you want to get a flatter voltage. What do you do about this equation? You increase the capacitance, because if you increase the capacitance, what?
Increase the capacitance or the frequency.
Yes, because if you increase frequency, what happens? If you increase frequency, then I'm doing this like this and this fast, for example, a lot faster. Right? If I do this a lot faster, this is my initial condition. Right? Now what does my waveform look like? I go up here, and then I go down here, up here, down here, up here, down here. So now this is now your ripple. This is your delta VC, the new delta VC. Right? So by increasing the frequency of your current waveform in and out of the capacitor, for the same value of capacitor, you were able to decrease ripple. The other way to do it is increase capacitance. Yes, sir.
Remember we used to put a Zener diode so we can get rid of the ripple, like a voltage regulator.
Yeah, you don't get. I mean, Zener diode. What does Zener diode do, right? Zeners, it's a diode operating in breakdown mode, right? So it's a voltage regulator. But if you remember from your 325, that Zener diodes don't. You cannot just put a Zener diode. Okay, I have over voltages, then I put a Zener diode, right? Because Zener diodes, they have a Zener operating, Zener breakdown voltage. So this is your, if you remember 325, this is V Zener, right? And this was the knee. If you remember, anytime you were getting close to the knee, you were no longer operating in the Zener mode, right? So, so it depends on the value of current. So you can have a voltage, but it will depend on your load as well. Yeah, I think if you remember what you were doing there, you had maybe a Zener diode here, and then you had a load here, and they kept, in the examples, we kept changing the value of the load, and if you increase the resistor, you decrease the current. If you decrease the current, this is current. If you decrease the current, then you're going up closer to the knee here. If you go up closer to the knee, this is not a Zener diode anymore, right? It's just an open circuit in that case, so it's not very useful. So we will talk about how to apply capacitors and to eliminate for filtering applications. Yeah. So we have a few minutes, 2 minutes, 3 minutes. So filters, important, right? Very important. We'll talk a lot about filters. Yeah. And then again, we don't want Bishoy to be sitting there all the time and with Mariam telling him what the voltage is. Because again, how fast do you open and close here in this integration? We kept the switch on for T/3 of the full period T. This T is called switching period. This capital T is switching period. So you kept the switch on for T/3, 1/3 of the switching period, to produce 3 volts. But what if the load changes? You would like to change the amount of time the switch is on so that you can maintain 3 volts. So how do you do that? You put a sensor, measures this voltage, and this sensor goes, it's talking to a small processor or analog circuit or digital circuit to control the device. So, don't stay on for T/3, stay on for T/4. Don't stay for T/3, stay on for T/8, depending on your load, because you would like to maintain an output of 3 volts. So in power electronics, there is a lot of control theory that is important. Yeah. So at the end of this course, if you're taking 420 now, it's great, because who's taking 420 now? That's good, because Dr. Hazem will go through control, and then he will go through simple electrical circuits, and he will sort of introduce control on simple electrical circuits. Where you would like to control the current, for example, here. How do you do that in this circuit? What we will do at the end of this course is make these power converters look like an electrical circuit. Okay? They're not electrical circuits, simple electrical circuits, because they have these switches, right? You don't know how to deal with. We know how to deal with circuits from 214, right? You know, if you have L's, C's, dependent sources, and independent sources, we can come up with a Laplace equation and come up with a transfer function, right? But we don't know how to deal with a switch, right? Switches we don't know how to deal with. So we will figure out a way to convert the switch into a model that will be equivalent to a linear circuit that you know how to deal with, and now give you a linear circuit that you've studied in 420 how to control. So at the end of the day, this linear circuit we will come up with will be in terms of the control signal for the switch. It will be a variable. It's called duty cycle. And then this duty cycle is something that you will control like you will control anything in 420. So we will deliver something at the end of the course that you will be able to utilize based on knowledge from 420. So we'll stop here. I think next class we'll start getting into circuits. So